Okay, good afternoon, good morning, good evening, depending where are you now. So today we're going to have our second lecture of social media computing and multimedia computing course. I'm Aleks Farseev, and today we are going to talk about text analysis and classification. So text analysis and classification is basically a very important topic in many areas, because text is everywhere. It's in social media, it's in traditional media, it's in all the media types we have seen. And even though nowadays there's a huge trend towards multimedia data, text is still one of the most major way people communicate. And therefore, we need to know how to analyze. And today's model is just about that. And it's also about some background knowledge related to machine learning. So the main purpose of this lecture is to give you some background on text analysis, to introduce some machine learning frameworks, to highlight the differences between information retrieval and text classification, and give you some insight on evaluation measures that you're going to use. I cannot be too detailed in each of the topics we'll be covering, because today's lecture is very dense in terms of materials, but I'll be providing you some references that you can look in. So these are the books and papers you can read. And also I'll be giving you slides and tutorials on today's lecture material, so that you'll be able to really grasp and understand a bit of more details about today's lecture by yourself. Then later you can use it in your labs, you can use it in your whatever type of work you're doing. So let's start. And we're going to start from defining what is free text, because we are social media computing course, right? So we're going to work with a lot of so-called free text and also retrieval of the text. Those jobs that Google's, Yandex's, and other search engines and search systems doing a lot on a daily basis to provide the key features. So what is a free text? Free text basically is some unstructured text. So it's something that is not controlled by a particular vocabulary. It can be a post on social media, it can be a research article, it can be a book, and especially for us, it's very interesting to talk about really those free texts like tweets. We'll be working with them a lot. So this kind of information needs to be analyzed and indexed in order to make sense of it. And this is a task that most of social media and search engines are doing in 24 hours, 7 days per week, just because this is a key, the heart of their business, the heart of their algorithms and engines. And of course, in contrary, non-free text could be something like what you can see in the bottom. So it can be, let's say, just some information about the passport of the person, some information about the name, gender, age. So those kind of information that you'll find inside the databases. This is not free text, right? It's still textual data. Let's say our name, right? But it's not free text because it is structured. It's always consists of name, a family name, maybe one more part, depending on the country where you live. So we need to analyze this free text. And of course, the general problem that we are facing is how to represent it. So how to extract those features that represent the text, how to distinguish one document from another, and figure out which documents are considered to be relevant to our queries. So this is information retrieval problem. And also how to group common set of documents in the same category. This is classification problem, right? Text classification problem. If you talk about data representation, the commonly used features are the linguistic features, linguistic units, so it's usually related to natural language processing, some named entities, some maybe even words or word statistics or phrase statistics, called n-grams, b-grams, etc. and different specific algorithms such as string, that's like particular data representations, but other more comprehensive algorithms to handle that. So, and you know, surprisingly, when it comes to research, I mean, of course, we do a lot of this kind of new complex algorithms to publish our papers. But if you look into what is used really in industry, you might see that the companies like Rakuten, so Japanese huge e-commerce vendor, main competitor of Amazon, they're still using a very, very simple representations of the data because of special properties such as evolution of the speech, because it's ad hoc, because you can process it on the fly. So many people just use, many companies just use the just a single term representation as a features, and it works quite well, surprisingly, and it's still state-of-the-art approach. But although if you just want to talk about what's the difference between retrieval and how you define these two problems, you would say the retrieval is when we have, let's say, a query, and we want to have a load of text. I want to match which particular text this query is most relevant. But when it comes to, let's say, classification, and we have many texts, and we want to figure out which particular class this text get assigned, this text belongs to. So this is the classification problem. Very different. When it comes to Google, it's definitely information retrieval, because we input query and then we see the results in the list according to the relevance. Hopefully, yeah. When it comes to, let's say, Facebook, when Facebook triggers the inappropriate content, let's say hate speech, let's say inappropriate judgments. So, for example, recent news, that is a text classification problem. So we have kind of classes, let's say inappropriate speech, and then we want to classify text on Facebook, figuring out whether this text is proper or improper. So this is the difference. So just one example. So we have a free text page. To obtain more accuracy in search, additional information might be needed, such as justness and frequency information, be useful, blah, 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 blah. So this kind of text can be represented actually by word counts, because you can see that, let's say, word information has occurred 3 times. And then we have also words and word, accuracy, search, justness, frequency, inverted, file, location, implemented. And you can build this kind of list. You can build this kind of list for the text, and this is called word count. And this counts basically tell us about what are the different frequencies of different terms. And then these frequencies can be put into the long table, and this table will be our data representation. This already can be used in this way. Intuitively, when you work with this kind of systems, it suggests that high frequency terms are less or even not discriminating, and low and medium frequency terms are actually more useful to enhance the precision for information retrieval tasks. Why is that? Yeah, you will be asking, why is that? It's simply because when we search a query, let's say, I don't know, Vladimir Putin met Belarus president, right? This kind of query. I guess if you look into just word Vladimir, is very common, but there's many Vladimirs. And if you look like met or visit, it's even more common word. So not very useful. The key semantics of this query is that it's Putin, and that it is Belarus, because the word president is also many presidents, different countries, but Belarus president is only one. So these low frequency terms like Putin, like Belarus, those keywords that help Google and Yandex really figure out what are the key relevant documents, there's the news articles really bind into this query. Yeah, so this is quite intuitive. Yeah. And of course, if you want to select the terms, you want to eliminate high frequency terms, and you will use the remaining terms to index. And you could even have a stop words list. So stop words are basically those words that are too common for the language. So for example, okay, I mean, in the phrase I give you, there's no stop words, I guess, but if you have a phrase, Vladimir Putin is Russian president, and he has visited Belarus to visit Belarusian president, then is will be a stop word. It's something that doesn't bring any semantic meaning with the query. You can just cut it, and then this kind of words will help you to eliminate and reduce complexity of your queries and of your computation when you start trying to match the queries one to another. And one of the stop lists you can see in a slide, actually you can just copy it and use in your code already. But of course, this type of stop words list is very limited, right? So you probably want to go on Google, find your list with a couple of thousand of keywords that you can use later for your stop words, for your work, for your algorithms. And you know, you already learned the first technique you can use, stop words. Yeah, remember this stop words is quite basic and important information retrieval techniques. But of course, you can also weigh the terms, and precision is better served by features that accrue frequency in a small numbers of documents. And one of such measures that is commonly used is called inverted or inverted document frequency, where you have total number of documents in a collection, and also you have a number of documents to which term K is assigned to, belongs to. Yeah, so then you can see inversely how many documents the term occurs. So if a term is rare, it will occur in less documents. Terms often occurs in more documents, so that the score will basically favors the term that appears in less number of docs, and then it will not favor the scores that this term appeared more often. So you can see if gamma appears in 900 documents, the rate frequency is lower. And then alpha appears on the 100 docs, and then the weight of this term will be higher, right? So this is how we can incorporate this, the logic of weighted terms into our data representation. It will help. And inverted decrement frequency helps in precision, while the term frequency, that's actually how often term happen in particular document, is helping in recall. I'll tell you what is recall with precision in the end, but for now, you just need to learn that there is also combined metric called TF-IDF, weighting schema, that basically incorporates both of this metric inside one schema, and then can provide you very, very nice weighting schema for your keywords that you can use in your algorithms to do information retrieval. And TF-IDF is very widely known metric. This was also applied in the first version of Google. And this is something you would really want to use, that incorporates both term frequency and inverse document frequency, and really help you to weight terms to search for documents that are relevant to your query in a better way. There is also something called term normalization, and basically you can just go to the previous example, and you can get this word counts. So we can remove some of the words that have occurred many times, and we can remove them by stop word list, right? It's just I mentioned earlier. So then it will be much easier for us to only count the meaningful words, but not all words that appear in the standard text. So what are the possible problems with the text pattern that can get generated? One problem, of course, is that this metric is bind to particular stop words lists, right? So if it's not up to date, or if it doesn't fit your domain, let's say you use stop word from scientific text, but then you go into social media and you're getting something it might not fit, you might not eliminate all. Another problem is that you could just remove some important keywords from the text by leveraging this, because not all stop words are ideal, and you might remove some meaning from some phrases, let's say. So these are the problems. And if you look into other possible problems that you can see in this example, you can see actually that in our original text, we have several versions of actually the same word. And in case if words in word would be counted as one, then the frequency of word will be 2. And also the frequency of adjacency and adjacent will be also 2. And there will be different weights assigned to this course for information retrieval problem. So the whole algorithm will work differently. But because our current approach doesn't know how to distinguish words and word or adjacency and adjacent, we cannot really distinguish them. So in order to mitigate this, we have the next problem. So what is a difference of different versions of the form and how to normalize how to normalize the words in order to be able to make them look the same for the algorithm, so that the countings and feature extraction can work in a proper way. Yeah, so you can actually think of even other ways of normalization and other forms of normalization that is needed. It could be your home assignment. Just take a look at the text and see what else can be done with this text in order to make it work better. But overall, the simplest way to tackle this problem is to do so-called stemming. Stemming is a way of algorithms that bring the terms into the same form. Yeah, so you have words recognized, 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 recognition, and so on. They will all will be bring to the same form, which will be something like recogn or something like that, and then cessation in will be removed. Suffixes or endings will be removed. Yeah, so it might change the meaning of the word for a human, and this is a disadvantage. So like you cannot really use your stemmed words inside your user interfaces to show to your final user of your information retrieval system. But for computer, it's just right, because if you have 4 different forms of the word to recognize, and each of them will be counted as 1, these words will be considered to be low frequency and therefore is important for information retrieval, for distinguishing documents. But the reality is that they're all the same, so they're actually not important because the frequency is quite high. And this is what you don't want to happen in your information retrieval problem. So there is a Smile steamer. You can just go to this link and try to see how the steamer will change the words. But overall, you have steamers in pretty much all NLP libraries in Python and other systems that you can use. So just use steamer every time along with the stop word normalization, stop words lists. So if you put all together for information retrieval, you aiming at extracting unique terms for documents, and you want to remove stop words and normalize terms. You could also use some thesaurus to find and group the low frequency terms. So for example, those words that are similar in meaning, but they're not the same words, they're synonyms. And you probably want to group them into one count and also eliminate them in case if they're too similar. Or you can form up phrases. You can combine high frequency terms together to form a phrases so that they will be lower frequency and therefore they can be more useful for you. Or you can use TF, IDF, or just TF or just IDF weights to assign weights to your terms, and therefore later when you'll be computing the distances between the query and the document, this weights will affect how you compute the distance and therefore affect your results. Hopefully it will help to have a better performance of your information retrieval system. So you, of course, have to do the same for query. Yeah, I mean, okay, this is quite obvious, but it's worth mentioning. Everything you do for your documents has to be done for the query as well. And that's what we're going to do. The similarity measures between your query and your document can be cosine similarity. This is you can just find in linear algebra and discrete mathematics, and this is a good measure. Can be other measures, and different measures are more useful for different scenarios. Some measures, for example, are more sensitive to particular spikes in frequencies of terms or TF-IDFs, Some are more widely used, like cosine similarity. There's also Manhattan distance. There's also Chebyshev distances, and many distances you can try to see which one works better for your information retrieval system. So we just usually use cosine as a default. And in most of the packages, you'll see cosine as a good system. So if you give example, we have information retrieval as query, and you have documents, information retrieval by versus retrieval methods, information theory forms of basic probabilistic methods. He retrieves his money from the safe. Yeah, so this is just a number of different approaches, the different documents, and one information retrieval query. And then you will be representing your documents by words that are used for retrieve, method, theory, VS, form, basis, probability, money, safe. You can see that probability has been extracted from probabilistic, so the stemming has been applied. And you can also see that words like by, words like z, for have been eliminated. This has happened during the stop words removal. So then you can look at the document as a frequencies. So basically, every time you have particular word occur in certain document, you put it as 1. If it's occurred more than once, you put it as 2, 3, 4, 5, etc. Is a frequency of the word. Non-normalized, yeah, non-normalized. It's just for simplicity, we don't normalize them. Then you can compare query with documents through the cosine similarity. And you can see that you can use other distances, you can use correlation, etc. So you can see that the distance between query and document 1 is 3, query and document 2 is 1, query and document 3 is 1, right? So basically what it says, it means that document 2 and document 3 is less similar to the query as compared to document 1, right? Because this is a similarity. But you also can talk about distance. So in this case, you'll be looking for the most lower number, because lower the distance, more similar the documents. Yeah. In information retrieval, we usually deal with the similarities. That's why it's used the similarity inside the slide. So this is how it will work in this example, and we decided, okay, D1 is much more similar to the queries than D2 and D3. There are many other ways, as probabilistic models, as models like BM25, language models, and you can, of course, go beyond the text as well. You can incorporate links, some social media sensors like likes. You can use ports of speech. You can use go further into recommendation systems, which is pretty much also information retrieval problem, but you're recommending items rather than documents, and your query is some explicit and implicit actions inside the system. So you're recommending items based on actions of the user. You can use a topic model. One of them called, for example, latent directly allocation. That also help you to extract the topics from your documents. Many other things. Yeah. We encourage you to go deeper in this topic, try to figure out what other features and models can be used for information retrieval, especially in case if your this year project will be related to building information retrieval or recommender systems. So in our models, especially when it's a little bit more heavier slides and materials, I will be making a 3-minute breaks between different sections, or maybe 1 to 2 times per lecture. So let's have a break. Let's come back in 3 minutes. Okay, so let's continue. So far we have discussed about the free text analysis and retrieval. This is a very important topic that is about information retrieval systems, and it's used in many recommender systems and search engines nowadays. But how about classification? And what is so different from classification and retrieval? How we look at this problem, how we treat this problem, and how do we approach to solve this by the power of machine learning. So text classification is pretty much about assignment of some very important predefined categories to free text documents. And what are these categories? These categories are called classes. So we have some M categories. You have N documents, and definitely our N is way bigger than M, the number of our categories. Yeah, and our task is to determine the chance, the probability that one of most categories is present in a document. So basically it tells what is this, which categories this document belong to. And yeah, as I said before, example could be whether this Facebook post is promotes some violent or forbidden content or not, whether advertisement on Google goes against the quality standards or, let's say, brand guidelines for particular brand or not, whether particular guy have a positive sentiment of the message or negative sentiment, so that, let's say, some government authorities can react and find whether there are some moments that they want to improve their services, their work for people, right? Like a sentiment analysis is another quite common way, quite a common approach and application of text classification. So applications multitude, and there's also many methods to do this. And you know from your machine learning course, there's no free lunch. So of course, for different text classification approaches, we have to use different classifiers. I will be just describing a few of them for the sake of time, but feel free to refer to your machine learning lecture notes in your another module, to your Google tutorials, etc., find the best classifiers that solves your problem. This is very important, and I will be talking about more how does this holistically work as a framework rather than about particular machine learning models that you could already know from your past experience. So, okay, first of all, is a dimensionality curse. You probably have heard about it. It's when you have basically too many. I mean, if it's a live lecture, I probably will ask you what is that. But overall, let's put it this way: we use features, right, for our classification, and we might get a problem of very high dimensionality of the features. Typical systems for information retrieval, but also classification, deal with tens of thousands of terms, right? And these terms can be dimensions if we just count the words. So we need to much more training data, train our system to distinguish the different documents of a high dimensionality. And we need more sophisticated models. We might overfit these models if our dimensionality is too high and many frequencies are low. And this is pretty much a problem, not just for text classification, but also for information retrieval problem as well. If our dimension is too high, it's really very hard to get enough of data to differentiate different types of document in this super huge, sparse, high dimensional vector. And of course, you can reduce dimensionality. You can do it very aggressive way. You can just cut a lot of keywords that are of low frequency, specifically for classification, or cut keywords at a high frequency for information retrieval task. Or you can also employ some learning methods to do some learning methods, some another machine learning that can actually help you to deal with this high dimensionality. One of them, for example, called PCA, right? You can really significantly reduce the number of dimensions by projecting features into another space mathematically, where all the features still contain the variance of your data, but the dimension is much lower and they're all orthogonal to each other. It's like principal component space. This is one way to do it. You have to minimize some objective function to perform this, and you can minimize your objective function for other different things. Use your SVD as one approach and many others. We'll be talking about this. But another way is to do a feature selection, right? So the aim of feature selection is to remove some features that have a little influence on the categorization task. Well, basically, if we have a document that wants to distinguish whether this text is about animals or not about animals, words like dog, cat, bird, cage would be quite useful. You don't want to remove these features from your data. But some words related to, let's say, I don't know, recent political news, well, they could be related to animals in some cases, right? But overall, this is not very correlated thing. So these feature selection algorithms might eliminate this kind of semantically not related features because they're not related to the task. And this is very good. This is what we want to use. And we, of course, want to also examine different methods, but also the criteria that affect this. So if information retrieval favors rare features and retains some non-trivial terms, which you can use for, you can use IDF metric to select rare terms. Text classification is more common features in each category. So document frequency, basically how often term is associated with the documents, become much more important than inverse document frequency. So if you have a document frequency as a function for a particular term, so number of documents containing the term TK at least once, information retrieval will give high weights to the terms with a low document frequency through the IDF inverse document weight. But how about text classification? Well, in text classification, that's opposite, and you would even want to come up with some threshold that will be cutting all the words where the document frequency of term is too low. So you want to basically keep the terms that are represented in most of the documents, so that in this space you can differentiate documents between each other, and then you hopefully can train an algorithm that can, or mathematical model that can distinguish those keywords that are, let's say, related to animals, those documents that are related to animals, and those documents that are not related to animals. So this is how it works, yeah, just like in the fingers in a sense. Of course, advantage is that it's quite simple, it scales well, and again, surprisingly, it performs well in many scenarios. And of course, it's ad hoc approach. So I guess the most disadvantage of this is that you never really know how you can control this, how you pick up the right threshold, and where it is the border of your performance, and how well you're doing this. It's hard for you to evaluate, which is pretty much common for many algorithms in machine learning. There is other term selection methods. It can be term strengths. For example, importance of the term can be evaluated based on how commonly a term is likely to appear in a closely related documents. So this definition of related documents come in. Yeah, then we are not that straightforward and linear by just cutting the terms. And it's a global category agnostic measure. So you have to bind this approach into particular classification task, and you can use a principal component analysis that I have mentioned earlier that is just use these the principal components to project into orthogonal space. You can use information gain, which is from information theory approaches. I know you guys have this course as well in the masters in ITMO by Kudryashov, so you can ask them about these approaches as well. It's quite interesting field and it's very, very useful to incorporate as well. And many others, yeah. Just Google it, you'll see many of these. And since text classification and classification methods are quite bind together, I probably will combine the previous chapter and this chapter and just go into classification methods straight. So what is classification method and what these kind of methods can be used? Once we select the feature set, the next problem we face is how to build this, magic model that can assign the labels to the new text, how to train this classifier. And there are many classification algorithms that you have heard about. I wouldn't be going too deep, guys. I assume you know all this. So I just blaze this through, but feel free to reach to our research assistants on the details of each of this algorithm. Or you can just drop me a line in Telegram and I'll help you to figure out how it works. So we'll be talking about naive bias, key nearest neighbors, support vector machines, SVMs, decision trees, the ensemble models such as random forest, but of course you can use your neural network that you learn it more so much, and many other algorithms can be used. The idea would be pretty much the same, and of course we are looking in a supervised learning algorithms here. Issues you will face as regular machine learning issues. It's parameter tuning, or maybe your category distribution can be skewed to particular labels so that you'll have to balance it before you train, you have to do oversampling, etc. Many other problems. So we have overall a training stage. So give of the training document sets DI from Y to N. You want to and also the training ground truths. So it's basically the labels for these categories. Let's say animal, not animal, and etc. You want to figure out the proper model to train this model to do the predictions. So you will be doing the pre-processing the same way as we discussed for information retrieval. You struct all words, you categorize them into lowercase. Yeah, this is also quite useful. It's one of the normalization techniques. You remove stop words, you will do steaming. You apply some feature selection method to reduce the dimension, or some of your algorithms, let's say regularized regressions, regularized neural networks, can actually do feature selection on the fly when they learn the weights. So it's a combination, but regardless what you choose, sequentially or inside the model, feature selection is very important in text classification tasks, so you need to focus on it as well. And after that, you can start employing your classifier to perform the training, or call it learning, or whatever, all those fancy AI terms. But you're gonna train your model. You're gonna to infer the particular shape of your mathematical function or a complex function, which is a neural network out of many layers, that will fit this data, not overfit, not underfit, but just fit nicely to solve your problem. And then this classifier can be later used to do the inference. So the classification process is called also testing operation stage. When you're given a test document X, you don't know the label of the X, but you can pre-process this X the same way as you was pre-processing during the training stage. You can retain only words in the dictionary extracted in the training stage. Like you cannot try to classify based on the new words. You only have to use also in training stage, and you have to use the classifiers with category threshold to perform the classification. You can see immediately a disadvantage of point number 3, right? If your text evolves so much, like it's in social networks, you cannot really train classifier today and then use it for the next couple of years, right? You have to keep retraining it, or you have to employ some online classifier that continuously gets a new keywords into perspective to be always relevant. And this is one of the major problems Facebook is now facing when classification algorithms, because they say, okay, today I train classifier, tomorrow it doesn't work anymore, and they have to come on with so-called online learning models. Yeah, but by the way, this is already a little bit of deep discussion, and just let's introduce a couple of the basic classifiers. So all of us know from maths the bias theorem. You can see it in the picture, the way of getting a probability of A given that P is true. So it's a conditional probability. And then based on the bias theorem, which you can find a proof on the internet, it also says that probability of A given that B is true is actually can be probability of B given A is true times the probability of B divided by probability of A, right? This is very useful features. And there's also one important property. I usually ask students what is that, but I just let you know now. So these variables have to be independent, right? In case if you want to apply it. And it's one of the important assumptions for the bias theorem. So that if you have this and you put in an example, you can basically put it like this. So if probability of boy given that the name is John, it's probability of John given as boy, probability of John divided by probability of boy, right? So that's how it can be decomposed back. I think this theorem is also very often used in information theory, so we are very familiar with it. So so then if you put it in numbers, you can see example below. Yeah, so you can just put in exact numbers and probability. You can see the probability of boy being named John is 0.02, 2%. In case if probability of John is 0.01%, and is about half of the population is boys. And if name is John, that's definitely a boy, right? So this is how it works. Very useful and widely accepted theorem. So probability of A or probability of B is called the prior probability. So you need to use these two priors, and it's what we know, or we can estimate, we feel that we know with some evidence. And then there's also conditional probability of A given that B is happened, not just likelihood of A. And this often can be measured precisely from the data that we have. And this also comes from your model assumption. And we also have posterior probability, which is vice versa to conditional probability, right? So of B given A. And this is answer what we want. This is something that we want to predict. And of course, if you put garbage in, bias theorem and bias classifier will output the garbage out as well, right? So it's very sensitive to the data. And that's why it's called GGO liability, right? Just like a little bit of jargon for machine learning. G is a garbage. So this can be applied to text categorization. So given a document and a set of classes, you want to find out the most likely class C that D belong to, right? So basically out of all the classes, figure out which one is most likely to be the class for the document DI. And you don't have enough data to do this, right? If you want to purely follow the bias theorem, right? Because it's very hard for you to estimate the probability of D given CJ, right? But we can estimate the rest of the probabilities, and we can estimate this from the data. So why don't we do that? We apply the bias theorem as it was described in the previous slide, and then we can reformulate. Then we can get the results. So naive bias classifier will be just pretty much direct application of the bias theorem, and there will be also one very important assumption. That's why I call naive bias classifier, that the features are generated independently given CJ. Then the joint probability of this will be a probability of x of the features represented in the document, and then you can just compute them by multiplying the probabilities one to another. So if we don't have this assumption, then computation will be very complex. But if we have this assumption that all the features are independent, then all of their probabilities will be equal, so we can ignore them as a multiplier. And then this is why naive Bayes is so fast and so easy, and you can just pick up the class that maximizes this formulation at the bottom. Don't have too much time to go into details, but try to figure it out at home. Read it through again and try to find the biggest difference between naive Bayes classifier and the direct application of Bayes theorem. So try to figure out and understand what I was just meaning when I was explaining this. So you have to estimate the parameters. Of course, you need to get estimates of the probabilities. So you need to estimate the probability of the class CJ, and you also need to estimate the conditional probability of the feature X given the class CJ, right? And you have, so capital X is usually a feature set, right? So you have to estimate the probabilities of the whole vector. And because they're independent, they can be estimated each one by one. You don't need to combine all of them together. So once you estimate these numbers, which is pretty much very related to counts, you can have these probabilities. Then you can apply the naive Bayes classifier. So given a training set of 12 documents and NJ3, the set that belongs to the class CJ, you can also compute the probabilities. And given the document 3, we can estimate the probability of the CXJ as above. So you can see just the different probabilities for different words. And then you can find the probabilities which is higher, and then eventually you can get the you can get the final response of for your inference for the Bayes classifier. There is also something called Laplace smoothing, and Laplace smoothing is important because the count of data is only approximation of probabilities, right? And count of 0 is quite problematic, right? Because if we have a zero values, and we can get division by 0 in certain cases. So basically, Laplace smoothing helps you to avoid this problem and add some constants to the both parts of the formula, and it pushes probability towards a prior of A divided by B. So basically, just like a hook or hack that you can use to eliminate the 0 counts in a training stage. You can look about Laplace smoothing when you Google Laplace smoothing for naive Bayes theorem. So overall classifier will be maximizing this objective function. So we'll be looking for the maximum value of the probability of the class given the document. And for the multi-class assignment, you can also have some category specific threshold that you can use to minimize the training error. This, for example, can also affect and reflect how often particular categories can be chosen for can occur in particular situations, right? So category-specific thresholds are quite often used in application of Bayes theorem for the multi-class classification problem. It's a simple and fast algorithm. Numerically, it behaves very well, but if your data is very sparse, and this will happen in case your representation is just a word vector and you don't do feature selection. Combinations of independent terms will be happening quite rare, and because these combinations happen where a lot of probabilities will be 0, so you might not be able to train your naive Bayes classifier efficiently. So naive Bayes works pretty well, sometimes state-of-the-art performance when your feature spaces are not that big, and features are not that sparse. And it cannot model some particular patterns, nonlinear patterns as a data, and it's not that accurate as compared to other methods. But again, there are some problems when naive Bayes working very well compared to linear models and sometimes even neural networks. So it's always good to try it and see how it works. So there's another classifier called K-nearest neighbor classifier. Graphically, it works in this way. If you represent your points on one plane in two-dimensional space, and you would put them in different colors according to each color represents basically the class. So we have two classes, orange class and green class. If you have a test document get compared to the classes that are near. That's why it's called nearest neighbors. And then if these nearest neighbors all belong to, let's say, a green class, then the TOS document will be also assigned to the green class. And you can use all types of the similarity measures that we discussed earlier. It can be cosine similarity, Manhattan distance, etc., etc. Have to be used similarity measures. And yeah, distance and similarity is actually quite mutually replaceable, because 1 divided by distance will be actually related to your similarity, right? So that's what we used. So once you find these similar documents, you can decide that this document belongs to the green category because it's close to the green numbers. So given at least test document X, you can find nearest neighbors that are bigger than similarity threshold. You can find top K such numbers, and then you can decide which class your document belongs to. So decision rule can be mathematically written like this. But just now I explained to you how it works, so I hope you understand that we're just looking for neighbors and seeing what are the neighbors' labels. It's just like if you're living in a student dormitory and your neighbors in this dormitory are, let's say, all students, but some of them are also maybe girlfriends or boyfriends of the students that are not students. If you just count every single human that nearby to your dormitory, some of them might not be students, but most of them will be students. So by K-nearest neighbor classification, you are also very likely to be student. That's how nearest neighbor classifier will work in the literal neighbors in a student dormitory. I hope you can draw some parallel to the mathematical explanation of this. And we have some category-specific threshold. We can determine on the validation set of the documents, and then we can divide training documents into two sets. T set could be 80%, and V set, like validation set, remaining 20%. You can train the classifier using the training set. You can validate this set, adjust the category-specific threshold based on validation set. We still don't tap into test sets, so we are fine. And then we can customize the outputs of our classifier in such a way that it have different weights for different outputs. So that sometimes, if we know that we are in a university campus, most of people around will be students, right? So even if it's not a dormitory, most likely people around will be still students, so you can actually adjust some category threshold to the student label rather than to, let's say, non-student label. And then by doing this, your accuracy of your classifier probably will even improve, right? But this is, of course, problem specific. You need to have validation sets to do this. And yes, very important, you cannot tap into test set. You must use your training and validation sets to train your models, and you only can use your test set just for testing. I think it's obvious to you, most of you guys, but just I want to confirm that this is how it works, right? It's no different from information retrieval, text classification, or any other machine learning problem. So we can define that, and if we use a K-nearest neighbor classifier, we can use it in online manner. I think is the biggest advantage of this classifier is that it can actually incorporate all the newly learned information about the world in now around immediately. So, for example, you are in a dormitory students, it's a university campus. You don't need just train your model on the current student intake of the campus and then later use it. It might not work. You could actually incorporate all your new neighbors that come to the rooms in your dormitory nearby. They come in a new intake. There are new data points that you know that they are students. So by comparing yourself to all the students in the physical distance nearby, you can say that this guys actually contribute into the way your model inference, and you do it on online manner. You continuously learn of who are these people around you, and they keep getting into the rooms, others go back to home, and you continuously evolve your model of KNN classifier that help you to better classify the stuff. We also have support vector machines. Support vector machines, just very brief, it's an algorithm that helps you to find a hyperplane between sets of variables in a multi-dimensional space. In a two-dimensional space, hyperplane is just a line. In a multi-dimensional space, hyperplane is a multi-dimensional line. It's trying to split your label 1 from label B. And what are the support vectors are basically those data points in your training set that are those vectors that are the farthest from this line, right? Basically, the model is trying to find all types of these lines so that this line will maximize the distance between itself and other support vectors, and the rest of the points will be even further. That's why in the example, you can see there's 3 support vectors there. One is the orange one, dotted line, and then another one is 2 blue support vectors. And then in the middle, there's a hyperplane dividing them into 2. So there's algorithms that can help you to maximize this margin between the hyperplane and support vectors. That's how support vector machines work. You have also decision trees. Decision trees is another family of algorithms. Basically, these trees just can look like this. It's just those decision trees we could use. The question is, and true is basically true, F is false, etc. Our question is how to train these decision trees. And there are several approaches. There's a top-bottom approach and bottom-up approach. Usually decision tree takes the input of object or a situation described by a set of attributes and returns a decision, right? And then to do the inference, it actually follows this tree all the way down to provide the decision. And you have a depth of the tree, and these trees can be binary, can be not binary. So if there are k attributes, the decision tree might have up to 2 in the power of k nodes. And this is usually much too big in the practice, right? So we usually have incomplete trees. We have a smaller trees, and these smaller trees can help us to figure out our decision in an efficient way, but also they work well. We can greedily train these decision trees recursively, and you want to choose the best split of features in each node into the tree in order to figure out the best tree can predict our attributes. So a good attribute splits in examples into 2 subsets that ideally all positive or all negative, right? Ideally, this not really happens. So in the left side, you can see that the split is not ideal because we have all red, all green, and also something that green and red at the same time. And that means basically that if you want to split the, like if you have a classification problem and we want to split the restaurants based on the type, you might have both green and red labels in each type of the restaurant. So type is not like a really the best split, but if you want to split a decision whether we should go into a restaurant or not based on number of people sitting inside there, then it's already much easier, right? If we have so the tree on the left side. Yeah, so basically the right tree is not very useful and left tree is more useful, and it depends on which type of decision structure, which type of consideration we'll be taking to build this tree. There's also information theory example. We have an entropy, and it's defined as each node can be defined as each node based on the class breakdown. So we want to repeatedly maximize entropy. So basically maximize the level of each knowledge, new knowledge each split brings us to. And if we maximize this entropy on every split of our tree, then we can get a tree that basically in every step gain way more knowledge in order to reach us to the best classification decision in the end. And this is how the entropy is used. So we also have information gain measure. We basically, before the split, by particular split in the tree, our entropy can be measured as E in the formula based on the probabilities. And after the split, the entropy can be measured as difference between before the split and after the split. So information gain will be basically this change of the entropy before and after. And if you maximize this information gain on every split, then you can get the best results in terms of tree split. And generally, machine learning is all about optimization, right? So we can maximize the whatever measure, maybe information gain, and then it helps us to get the best result. So if we split by the features, like if you go back to our restaurant example, we split the data based on number of features before, so we can complete the interpretation, the information gain, and we will see there's no gain when we do the split. We still have A, B, and C, A, B, and C. But when we split by type of the restaurant feature, we can see that actually we're able to get some information gain. It's just 0.5 bits. So that binds back well to our original example of the splits, right? So it tells, okay, so this split is useful, and then you can further use it in training your classification model. So in each node, we choose attribute which maximizes information gain, right? We want to gain information every split. We don't want to have useless splits that will increase our computational complexity, and that wouldn't really help us to solve our task of classification. So this strategy will tend to produce a mixtures of classes at each node, and every time we do a more and more split, it will become a more and more pure understanding each of the features between the two classes we want to split our problem between two, right? Whether we go to a restaurant or we don't go to the restaurant. And if a node has examples of one class, we make it a leaf, output C, right? So once we reach the very bottom, then not only have types of one class and we don't have type of another class, and we make it a leaf. So if you don't want to overfit, meaning that you don't want to have each of your nodes have only one sample there, and it will be overfitting of the data. Then you also can use something so-called tree pruning, right? Which is another technique. Decision trees are very explainable because you can see the whole structure of the tree. You can see how classifier makes decisions, and that family of algorithms form the big chunk of so-called explainable AI approaches, right? So many of them are tree-based. And this also offers a systematic approach to select the best combination of features towards making a decision. So basically, does the feature selection on the fly. Well, the fifth family of algorithms I would like to propose is ensemble learning algorithms. And from the word ensemble, you can see that these algorithms basically leverage on the powers of multiple algorithms together in order to increase the results, in order to take advantage of all the algorithms that participate in the ensemble. So it's usually a collection of the hypotheses or results, and then combine the predictions of this. So we have many learners, and then we predict different models, and then we combine in the end to do a model combiner that is doing better results. And then final results can use weighted voting or majority voting or different other schemas like Bayesian or boosting to improve the results. So it's a little bit like a crowd-funded, crowd-sourced machine learning algorithms when many weak learners combine their efforts, vote for the results to come up with one strong learner that is really much better as compared to the individual learning results. There are several types of these algorithms, Bayesian algorithms to train learners in parallel on different samples of the data and then combine by voting together, like averages continuous input. Stacking is combining models' outputs and then use another learner at the second stage to let's say, do linear regression in the end to find the best combination, weighted combination of the outputs of classifiers. And we have boosting, trains learners on the filtered output of other learners. So basically it's trying to figure out which type of data samples other learners cannot figure out correctly, and then trying to learn other models on how to distinguish these two guys. A little bit like a decision tree, right? Every next step is trying to figure out how to distinguish things better. Our random forest is one of the state-of-the-art ensemble algorithms. It's pretty simple, but it's quite useful. And if you really want to check the state-of-the-art performance of your data set, you could consider random forest as one of the simple but powerful models you can use. It's consisting of beginning of unprompt decision tree learners with a randomized selection of features at each split. So basically, you have many trees, and these trees are trained based on different features. So, and these features are picked up randomly. So, so these trees grow on a data set sample from the original data set. So you're kind of getting a lot of models trained together on samples of the data, and these models also use different features. So if some of the features are not useful, they will not participate in all learnings, but participate only in particular cases. And then they will spoil performance of some classifiers, but the rest, all the users features, they will be doing well. And then assumption is that majority of classifiers together will be able to do a good decision. It's just like if all of you come to the classroom and ask you a question, maybe some of you are using Google to find an answer, somebody else using books, and somebody else, let's say, using a friend suggestion. And friend suggestion didn't really help, and maybe books were not as useful, but Google was very useful. So that's, if all of you finally decide to vote for the correct answer to my question, and if most of you were using Google, which is a good feature, then anyhow you guys can answer correctly, even though there was somebody who was trying to get an answer from a friend, or answer from the friend who didn't learn machine learning, or from maybe a book that is a little bit outdated. And then even though they have wrong performance, overall you guys will still do well. And that's how ensemble learning is working, particularly in case of random forests. Random forests are doing well. This is how it looks. You can read about this classifier, but I think I have explained to you the overall systems. They are very popular, they are easy to implement, and they can be paralleled. Why they can be paralleled? Because we have many trees and different samples of the data, so you just run all these things in parallel and combine together. They can be applied on the MapReduce, in a highly parallel systems in the clouds. Very, very useful algorithms. Yeah, so consider using it in your labs and in your final projects for this course. Well, The accuracy is always reasonable. If you compare, I mean, you might still find quite a bit of the papers when random forest did well, but of course, deep learning neural networks recently do a good job as well, right, for the many tasks. Of course, you need many passes over the data to maximize the depth of the trees. So this is the disadvantage. And then also random trees can be easily overfitted, right, for the data. So this you need to be careful. Even though they do the feature selection, if you choose hyperparameters wrongly, random forests could draw you into overfit, which you don't want to have. So you always need to make sure that you are doing really well generalization on your validation and in your test set. So to basically solve the problems is one thing, but how we understand that we did things correctly, how we evaluate our algorithms. There are a couple of evaluation measures that can be used. We want to also think about efficiency versus effectiveness of each of the algorithms we have algorithms we run. So efficiency is always about the speed and storage that is used by algorithm, but effectiveness is measured by the relevance. So that is, of course, about information retrieval and also classification approaches. So we always have retrieved and missed documents, information retrieval. We also have relevant and non-relevant documents. So if you combine all A, B, C, D, you get a total number of documents inside the database. So basically, relevant retrieved, relevant non-retrieved, relevant non-relevant retrieved, non-relevant not retrieved missed documents. So the precision will be A divided by B. So basically, number of relevant documents divided by total number of documents, and recall will be number of retrieved relevant documents divided by number of retrieved relevant documents plus missed relevant documents. Basically, recall is thinking about how many relevant documents he missed in your output, and precision is talking about out of what you output, how many relevant documents have been found. And of course, for different tasks, precision and recall have a different meaning. So I guess you would probably want to dig a little bit in the internet again on what's the difference between precision and recall, and for which tasks precisions are more important, for which task recall is more important. We also have combined measures. It's called F measure. The most commonly F measure is F2 measure, so the F1 measure, so the beta will be replaced by 1, so it will be 2pr divided by 2p plus r. So that's how it works, and this measure incorporates both precision and recall. So you can also see some variations. There's also average F1 measures that not just calculate the F1, but also calculate the average number between different labels, and that helps you to tackle the problem of imbalanced data sets when your some set of labels are much more likely to occur in your data as compared to other. Yeah, so for classification, we also want to account the skewness in the data evaluation, and that's why I have this micro F1 and macro F1. Macro F1 is average of the categories. It's the one I just explained. Micro F1 is average of 1 over all test documents. So basically, it's also considers the distributions. And characteristics that micro F1 tends to dominate the classifier's performance on common categories, and macro F1 is influenced by performance on the rare categories. So it's like a stricter measure. So usually, if you look into the in the papers and scientific papers, very often comment of reviewers is, hey, why don't you use a macro measure that really tells us how well your problem is solved, but not how well it solves classification tasks, given that your distribution is so skewed. But if your distribution is uniform, then there's no difference. Yeah, so let's say in gender classification, in general, it doesn't really matter. But when it comes to gender classification of, let's say, Pinterest users, where most of users are females, they start getting matter. You probably want to use a macro metric to classify. Yeah, so we also have average precision to evaluate systems in information retrieval and in recommended systems. You can see it all as well. So it's a precision at k times of relevance of the documents in the case position. So this measure basically also accounts on the position of document, but not just if it's relevant or not. Obviously, in Google, if we have result document in the first position is different than the capital 6th position, right? And we need to count on that. So it's a quite realistic measure that comes together with the industry problems. And then we also have NDCJ score, we have mean average precision, and many other different measures we want to consider and we want to use instead of just using simple ones like macro-F1. So it was a heavy lesson. I really encourage you to read the materials, go through the slides again, and prepare well for your tutorial that will be held next week after the lecture. I will be sending you the tutorial questions by the beginning of next week, and then you'll have a couple of days to prepare. Then you'll be able to go through the answers on the tutorials after the lecture with your research assistant on this course. And in this chapter, we discussed information retrieval and text classification, as well as some evaluation measures and results. While in the next lesson, we'll be talking about very exciting topic of microblog data analysis, so much more bind into our particular application of social media analytics. Thank you very much and have a good day. See you next week.